We get the recording turned on here. And this evening, we have special guests from the Arizona Near Space Research Group. Um, they they launch balloons and they go up to very high altitudes, and they have students they work with. And let me get a microphone for you so that you can be heard. And so we have Clayton Jacobs here, Stephen Thomas, and Dennis Campbell here in the room with us. And I think they're going to play tag team on presenting and tell us all about near space research. So please take it away.
Alrighty.
Can we jump into presentation mode?
I'm not big on presentation mode, so this is actually intentional, if people don't mind. There is a little bit, it won't stretch quite to the edge of the screen, but we can try it. I don't know if my laptop will take easily. Okay, it's looking okay. All right, we'll give it a shot tonight. Okay. Thank you for the introduction. Myself, Steve, and Dennis are here tonight, longtime members of ANSR and participants on the board. Who we are. If you don't know us, we are a 501c3 nonprofit. Our purpose is to promote science, or all STEM education through exploring frontiers in amateur radio and high altitude balloons. So the goal is promote these things by getting students involved, as well as those from our community, not just ham radio, but everybody if we can. And we are an affiliate organization of the Arizona Space Grant Consortium and a member of ARCA. So what we do, if you don't know, we do all sorts of things with high altitude balloons. So we are pre-flight planning, we are in-flight prediction and tracking, we are launch and recovery, and then post-flight data support if there is any of that sometimes. So our launches are funded through our educational partners, not necessarily through businesses, but primarily educational institutions, as well as we do for some public demonstrations. Hamfests help us in raising awareness for the organization because it gets us out in the public and everybody gets to see us. However, you know, our flights are for the students where there's not always a huge public viewing. And we're at over 150 balloons now. I don't know if we have an exact count of our numbered launches. We're at 156 as of this weekend when they are successful, fingers crossed. A little bit about funding, just so everyone knows. We are a nonprofit, so everything comes from grants, our member dues, and tax-deductible donations. So that's it. Where does the money go? Costs are primarily the equipment, the balloons, $400 a piece, tanks of gas. When it was helium, we were like $400 to $800 a tank, and now we're down to about $150 a tank, which is workable in our current budget. Some of the money goes to member reimbursements. If you're an ANSR member and you're paid up, we can help you with hotel costs if there's a long distance travel, or reimburse some fuel costs, or some of the swag and giveaway items that we have throughout the year. So we've got a little bit of a video to share. Not sure how this will translate over the Zoom, but we're going to give it a shot. I'm all muted here, so let me look for the magic button in the corner and see if audio will send. I believe so. Let's give it a shot. And I don't see a play. There we go. Okay, I don't see it. Let's see if I'm sharing audio as well. Ah, share sound was not there. Now we could try.
Only within the past 100 years has space exploration become possible for mankind. Today, space remains difficult and expensive to discover. year, Arizona Near Space Research makes it possible for more than 100 students to explore the edge of space using high-altitude balloons. Arizona Near Space Research is a nonprofit organization that promotes science, technology, education, and mathematics through amateur radio and high-altitude balloons.
We've always felt that students should be involved in our projects because it's a medium that it's got to start, it's got to finish. You can theorize, you can design, you can build, you can test, you can actually fly, and you can analyze the data, all in the matter of a semester.
When did we start building this? Like
ages ago.
a month and a half ago?
About a month.
So it's been like 6 weeks.
And we finished this morning.
To the
Yeah, we wrapped it in duct tape and we put fleece inside.
Okay.
Okay, a typical balloon flight, one involving students, would probably start very early where we have breakfast and we commute out to the launch site. Once we're there though, we try to get there an hour before launch. And so it takes about an hour to tie in the payloads, check everything, make sure that they're working, and then about 20 minutes till launch we'll start the balloon inflation.
Radios must be checked, the communication beacons must be prepared, and the balloon setup assembled for student satellite prototypes. Jack is unwinding the tow line. Student payloads will be attached with metal couplers approximately 10 feet apart on this line.
Put that loop through that top. We're going to put slack so the weight will be through the package on this rod, and then we'll do another one and do that on the bottom. Okay?
The most important payloads carried by the balloon are recovery beacons. Inside each recovery beacon, a GPS will transmit the coordinates of the balloon's position to the chase team on the ground. Other important payloads include cameras, both still and video. They collect visual data during the flight, which helps students better understand atmospheric conditions and the behavior of payloads in flight.
This box.
That was the last time that
payload. We got the camera. We got
was.
we got an accelerometer in there. We got a temperature sensor. But the main project with this box is these 4 booms we have attached, which are moment arms. And our goal is to dampen the rotation rate of the balloon sets on the string. So hopefully we'll stabilize the payloads enough that the cameras will get steady shots instead of it just all spinning around.
The inside has a series of insulative layers to hold all the heat in as it gets to higher altitudes. Our probe is equipped with a pressure sensor and 2 thermal probes, one to measure the temperature on the inside, the other to measure the atmospheric temperature on the outside. It also takes still shot images once every minute and a half, so every 90 seconds. It uses these pendulums here to try and stabilize its spin rate, as the system that it's floating on is rather chaotic.
High-altitude balloons are made of latex and filled with helium. It takes about 2 cylinders of helium to fill the balloon to a diameter of 8 feet.
The balloon can be anywhere from 12 to about maybe 16 foot in diameter at launch, and due to the pressure changes as it goes up, that balloon gets larger and larger.
A balloon with a diameter of 8 feet will lift 10 to 15 pounds of payload weight. A parachute is attached directly beneath the balloon to decrease the return velocity.
The parachute opens immediately, and you can see that in the video, but the air is so thin it's not very useful. And but then as the air gets denser, the parachute will be more and more effective, and it will slow it down. And by the time it reaches the ground, maybe 45 minutes later, it's traveling about 12 to 15 miles an hour.
Weights hung below the balloon match the calculated amount of lift so that it is easy to determine when the balloon has been filled with enough helium. When the weights begin rising off the ground, the gas is turned off and the balloon is capped. All the beacons are double-checked for proper function as they are solely responsible for the balloon's recovery. It is standard procedure to fly 2 to 3 beacons for safety. Last-minute instructions are given, and students take their positions on the launch line.
So once we have the balloon inflated and all the payloads are laid out, we'll essentially have the balloon upwind. So if the wind is going, say, that direction, all the payloads would be there so that the balloon will rise up, travel over them, and pick up the payloads.
So what we're trying to do is we're at least trying to line up with the wind. Everyone push a little that way.
We have launch of ANSR Flight 64.
The balloon usually travels anywhere from 800 to about 1,200 foot per minute. We can control that. That's the ascent rate by putting in either more or less helium. If we put in more helium, it goes up faster, but not as high, because once it reaches about 50 foot in diameter, the balloon will burst.
During the ascent, decreasing atmospheric pressure causes the balloon to expand to many times its original size. As the balloon continues its journey upward, temperatures fall below
As we come back, watch the size of that balloon in relation to those 4 prongs. You'll see it grow as you come back and forth.
Winds encountered in the jet stream cause the balloon to attain velocities over 100 miles per hour. A high-altitude balloon will rise to the very edge of space, allowing atmospheric sensors to collect data above 90,000 feet. Onboard camera payloads capture the beauty of planet Earth by taking photos and video throughout the flight. Typically, it will take about an hour and a half for the balloon to reach 90,000 feet. Even at this altitude, the balloon remains visible to the naked eye. The chase teams quickly pull over and try to spot the balloon in hopes of observing the burst. Directly after burst, the atmosphere is so thin the parachute will not be very effective. The packages fall, reaching velocities of over 100 miles per hour until 40,000 feet.
Most of our failures occur right there, and so we have to be structurally, sound and electrically, sound as well. And then it takes about 45 minutes for the balloon, for the payloads to parachute down.
In each chase vehicle, a special piece of equipment called a ham radio receiver is able to detect when the recovery beacons on board the balloon transmit a GPS coordinate.
But we have tracking beacons, and this is one of the tracking beacons that the students here at Embry-Riddle built. And it's essentially a GPS receiver, this little board here, and it goes over to a modem and then to a transmitter, and that sends down the GPS information. And so we have displays in our vehicles that will then take that GPS information, put it on like a map, including Google, Earth, and we can actually see where the balloon is.
Chase teams try to be within a few miles of the landing point prior to touchdown.
Okay, there's one.
Yeah, trying to find the balloon with some binoculars, over.
After the balloon has burst, the team has only 45 minutes before the payloads will be on the ground. The flight path is examined and drivers use road maps to help figure out the best route to the anticipated landing site.
Now this shows the road going back. You can see here, here's where we're at.
Yep.
Here's 300, here's where our balloon is. This shows a bigger road back here.
When the balloon has descended to an altitude of 1,000 feet, the recovery beacons transmit one last GPS coordinate before dropping out of range.
We've been within probably 50 feet of it landing a couple of times. One of our students, Elijah Brown, and I, we were out and he was driving and I told him, back up, back up, back up. And the balloon missed landing in the back of the pickup truck by about 25 feet. That was fun.
That way?
Just landed.
Out that way.
I copy you. I'm heading up.
Okay, we're 1 mile away from it.
Once the chase team is within a mile of the payloads, they are close enough the recovery beacons can transmit an exact GPS coordinate of the landing site. Students enter this coordinate into a handheld GPS and take off in search of their payloads. Professors aren't far behind. Students conduct a visual inspection of the landing site and their payloads.
I hope our chip's still in there.
Students cut their payloads free of the tow string and collect the data gathered during the flight.
They provided what they were supposed to upon launch.
The morning concludes with pictures, handshakes, and congratulations. The flight is complete when each team has recovered their payload and collected their data. Although the flight is over, for some students, it is just beginning.
For many, flying the balloon is not the end to itself. As I said, the students at the collegiate level are allowed to build the design and build their own payloads. And so they'll spend a full semester doing that, and maybe 2 semesters where they'll add on the second semester more complexity to their experiments that they're flying. Generally, we have pre-flight reviews, we'll have the flight, and then they will digest their information, and then we do the second semester, and at the end of the second semester flight, we will have a symposium. The symposium alternates between ASU and U of A, and there's where the students get up and talk about their results. And so there's some public speaking, and they talk about their design and then what the results were, and sometimes what they would do better next time.
These students are tomorrow's engineers and space scientists. Because of Arizona Near Space Research, these students were able to design a satellite prototype and send it to the edge of space. Anyone can become involved in high-altitude ballooning.
We're not the only group in the country. There's a number of groups now that are almost in every state. So if you'd like to get involved with that, Google Space Grant in your state and contact those people. And they probably have a balloon program within almost every state now.
We hope that you have enjoyed this program on high-altitude balloons. Please visit our website at www.ansr.org for more information.
Okay, so maybe the video was a tad bit old and we should redo it, but we're getting there. That's essentially exactly what we'll be seeing on any flight, but like our flight this weekend on Saturday, Similar student teams, similar launch and recovery process, just less snow. So let's talk about how a launch works. Similar to what you saw in the video, this is just some of the planning and prediction on ANSR's side before we get to the launch day. So the student teams build a payload to investigate atmospheric science or some kind of experiment that would show results in the near Earth environment. Sometimes we get Geiger counters, we get cameras, we get air sampling, we get seed or insect samples that get taken up. So all types of projects besides just temperature, pressure, that type of thing. And what does ANSR do? Well, we do a flight manifest, a support plan. We do predictions the week before the flight, if not more. And then we're actually there to support the launch and recovery process. So want to point out some of the things that we generate. One of Steve's main jobs as flight coordinator is to lay out all of the payloads onto a flight manifest and then try to swap payloads in between so that both of our balloons, because we have so many payloads, we need 2 balloons, so that both of our balloons, assuming they take off from the same place, land approximately at the same location. So starting a week or so before launch, we prepare a manifest in Excel, looks kind of like this, and we break the kids up into 2 teams, red flag and blue flags. So after a manifest is generated, then we look at a support plan. So how do we get all the bodies in places that we need in order to support the launch? That includes people at the launch site, but also people at the potential landing sites to help us get information that may be farther away that we won't get to in time. We can't drive fast enough. You can see there's a variety of jobs, everything from APRS digipeater equipment that are in play in people's vehicles. On this flight, ANSR 147, 148, we actually had an APRS aircraft available, somebody in their private plane to fly over and digipeat if we needed it or grab packets for us. So we've got a couple dedicated jobs like FAA coordination, somebody who does most of the phone calls to the different FAA centers. We've got equipment trailer that comes with us, usually towing behind my vehicle, and got one person, if not a couple people, that are dedicated to running predictions so that they know how our prediction tools work, as well as the internet-based ones, and how we input the data to get the result. Now down at the bottom, you can see a little bit of our comm plan. It's not highlighted here, but if we go to the next page, you can see on a typical flight, this is the RF technology that we're employing. So we've got our crossband balloon repeater that flies on our first balloon usually. We've got an alternate, a mountaintop repeater that we know will always work as a backup. And then simplex frequency is available for those that can't hit the repeater or might have an issue with equipment or something that, a little easier to talk back and forth. Beacon wise, with 2 balloons, there's at least 4 beacons in the air, and we split them up between 2 meters and 440 just for a little bit of redundancy. And then we've also got a CW beacon that operates on 2 meters that we can use to radio direction find if for whatever reason everything else has failed, and now we've got to go with some Morse code tapping to get us to the payload landing site. Everything's broadcast on APRS. You can type in aprs.fi in your address bar, type in our call sign with a little asterisk at the end, and you can see all of our beacons that are available. Okay, flight coordination. So we go into it a little deeper with the students, but I'll just mention that there are laws that regulate how we do balloons. If you're over 4 pounds, there's all sorts of laws that we are compliant to. The FAR 101. ANSR is compliant for non-exempt balloon flights, and we coordinate each of our flights with the FAA. We give them notice that we're going to do a flight, as well as we file the required NOTAMs, the notice to airmen that let other airplanes in the area know that we'll be there. And we also carry an ADS-B transponder that enables us to be seen by other aviation participants that have ADS-B receivers, as well as respond to Mode C location pings from the FAA for, what is that, secondary radar? Altitude. And then there is a radar reflector for primary if they wanted to do that, but okay. And the final piece of the puzzle for pre-flight is the predictions. So Steve, do you want to talk about predictions since you've been doing predictions so much lately?
So for the predictions, basically, as Clayton mentioned, we have the payloads from the students. We also have our tracking payloads and other equipment that flies on the balloon. So what we do is we take that weight, that gives us our manifest weight, and then we determine our lift, how much gas we're going to put in by a factor percentage over the weight. So in this case, this example is showing we have 18 pounds of payload and we're running 140% lift. So we're running 1.4 times the 18 pounds of lift, which is the 25.2 pounds. And what that does is that's we're putting gas in the balloon, enough gas in the balloon to lift 25 pounds. We've got a couple of ways we do that. One of them is we actually have a flow meter that we try to use where we have an idea of how much gas we need to put in. But the basic, what we do is we actually take 25 pounds of weight, barbell weights with an apparatus that the balloon is tied to, and we fill the balloon until it lifts that weight off the ground to a satisfactory bit. And that gives us our ascent rate. So the neck lift weight is how we determine how fast the balloon is going to go up. Ascent rate, in this case, is 1,500. So normally we fly 120% on a standard on our standard balloons, 120% weight of lift. But what we'll do is as we get into showing the predictions down here, if it's going into an unfavorable area or too far, we have ways to adjust that. And one of them is how much gas we put in. So in this particular case, we increased our lift to 140% because we wanted the balloon to go up quicker so that when it's in those layers of the jet stream and other winds, it's not in those layers as long, so it doesn't get affected by those winds. Burst altitude, we run this off of a data from the balloons we fly that a certain certain size balloon has a characteristic of bursting at a certain altitude based on how much gas is put into it. And then of course our descent rate is how fast we come down on the parachute. That one pretty much is a factor of how much weight we have based on the 8-foot parachute we did.
So using these assumptions plus the weather information for whatever that time is, if we look at the jet stream at that time, as it is essentially every year in November, it is east to west. So that was positive for that flight. And then when we look at the launch weather for that flight's morning, we saw relatively low winds. I mean, if it's over 5 miles an hour, we tend to hesitate, but I think this was a pretty good morning and, overall sunny. So let's get into the predictions.
So there is a website, sonhub.org. They have a prediction calculator on there. So we go to predict.sonhub.org. They've got these parameters over here. So that information that was on that previous one, we've determined what our lift's going to be. What we know what our GPS coordinates are going to be or where we want to launch from. And then we also know the altitude of where we're at and what the predicted burst altitude is and our ascent rate and our descent rates. So we put these factors into this calculator. And then what it does is it gives us a predicted track up to 7 days out. And so we usually start this 7 days prior and we start doing this every day. Now, when we look at this calculator, if that predicted landing area is unfavorable or is in a airspace we need to avoid, or is in an area that's very difficult for us to recover, like a canyon or woods with no road and stuff, then as I mentioned before, we have certain factors we can change. One of them obviously is we can put more gas in, that'll make it shorten up. We put less gas in, it can go longer. The other thing we can do is we can change our launch site. So if we needed this to move, or needed this to move to the east, and even after we shorten up the flight a little bit, then we would find a launch site that's a little more east of where we started from. So it's a game we play over the week prior.
And then not only does the tool generate this view for us, but we can export it into Google Earth. I think this is Google Earth Pro, but then we can visualize the flight path in 3D, you know, including mountains or whatever might be along the way in the process. Riverbeds or changing anything really. I think we've been using maps in real time during tracking as well, so that we can try to find, well, not all pathways that you see on maps are available when we actually get there. We've learned that many times. So
yeah, Google Earth satellite has come in very handy sometimes to figure out alternate paths into wherever we're landing. So the other thing we use with this map is once we get these predictions, we do one of these the morning of the flight based on where we're at and what we've determined. So what'll happen is of course, the group of us with the balloon and the gas and everything are going to go to the launch site, but there's going to be some of our members that are going to go up to that predicted landing area and sit in that area. And most of them have the capability of receiving the APRS beacons directly from the balloon, so that as the balloon comes down, we can get those packets near or on the ground to help us with recovery.
So you got to see during the video what a launch looks like. That was a launch with students filmed from the ground, but now let's look at one from another view. No audio here because we were up in a drone, but you get to see a good view of the kind of moments leading up to and then including launch, as well as the balloon slowly starting to drift out of sight. Looks graceful when you're not standing under it with your hardware connected to it.
Or when it gets released a little early and it comes swinging at you on the ground.
Actually, the swing I can demonstrate in this video a little bit. This was, again, another student launch from the Maricopa Ag Center, the landing strip over there. And you'll see the bottom payload as the balloon gets released. There's a large pendulum motion that we've got to watch out for when we have heavy payloads.
3, 2, 1, launch!
Hence the reason for the hard hats.
Yeah, we need to add the one. We had one time that when we launched, it got ripped out of the last person's hand before she was under it. And it missed the ground.
Near miss.
No, it did. Well, it didn't hit the ground, but it was coming right at me. And I basically had to pull my best matrix maneuver to get out of the way. We have it on video somewhere. One of these days we'll get it uploaded.
Chasing and recovery. So the last piece of the puzzle, once the balloon hits the ground or once we've released it and is heading towards its landing site, what do? All the students hop back in their vehicles with their drivers from the schools as well as ANSR, and we all start to follow the chase. We've got our ham radios and phones for whatever communication we need, as well as some of the students use a data connection to follow in real time. We work with everybody on kind of the plan as we move forward. We don't know where it lands or what the ownership of that land is in case it's private or tribal. We've always got to ask permission first, make sure we have enough equipment to actually hike in and hike out to get our equipment. We want to make sure that we photograph the payloads as they land in case there was some weirdness that happened in flight that we couldn't see. Can we capture it on the ground before we tear all the payloads apart? And then is there like a shutdown checklist or some way to safely power on or off your payload? Because we've learned with students that if you press the wrong button at the wrong time or don't turn off the payload in the right order, then your data sometimes goes missing. So we now recommend that they have something like that just so we can say we told you so. And then once we get our payloads back and hike back to the cars, the students will eat a lunch and then give us a quick debrief on what they thought their experiment did. Did it survive? Did they get some data, or are we going home empty-handed this time with just lessons learned?
Yeah. Also, during the chase, a lot of times we'll pick a location that's expected to be about mid-flight range that we can get to before expected burst. And it'll usually be a gas station or something that's got facilities for everybody. But what we'll do is we'll get there before burst and we'll actually try to see it. So it is, you know, as it's going up on a clearer day, you can actually see it at altitude, because as you noticed in the video earlier, as it goes up, the balloon is growing. So on the ground, it's 10, 15 feet in diameter. At burst, it's 50 to 60 feet in diameter. So you can actually, when you're looking up, you can see a little white dot, and we'll watch for it. And then when it bursts, you'll see that little white dot just fuzz out. So it's kind of cool to see it. What's really fun is when you're on the side of the road, you got 20, 30 people all staring up in the bit. And of course, since these are usually in the morning flights, we're all trying to block the sun with our hand. So you got 20 people sitting on the side of the road, all looking like they're, you know, worshiping the sun. So we've had people drive by us going, what the, but it's definitely fun to see the burst. And that also usually gives us an idea of if it's been close to the prediction or not. And then we can determine if we need to change where we're going to recover. What percentage is manual burst? In most of our cases, it's probably about 95, 96% manual burst where are you talking where we burst it? Oh, that's probably more like about 2%. We have flown cut downs before for bit, but we're still in the process of trying to develop a reliable one that we can cut down. Most of the time it's the balloon popping. When it doesn't pop, you can end up going a state or two away, right, Dennis? But we recovered it. We have done one of the ones is a chromium wire that the string runs through and up against that we can try to send a signal to, and the wire gets hot and cuts the string. That's had some
just pulling the string tight and the wrapping around it.
Right. Yeah. I mean, we've done it and with some success, it's worked, but it's as mentioned, if it's not against the wire properly, it doesn't always work. And you only have a few seconds of the heat before the batteries are exhausted. So we've been trying to work on different things. I know there's been some
because we can't use explosives like NASA does.
Right. Yeah, we're not.
They blow theirs with a.
Yeah, I mean, we've talked about everything from creating a neck that had spring-loaded blades to where we could send a signal that releases them and they pop open and cut it. To what was one somebody I think tried to came up
like a Dremel blade that was on a little motor.
Yeah, they're trying to cut the string. Let's see, we've had I think one of the designs, although we never flew it, involved a pellet gun barrel situation to try to shoot a projectile at the balloon to pop it. yeah. Oh yeah, well, so of course the other fun part about this is we are at the mercy of the gods and the winds, and sometimes they have a sense of humor. So we have in recent times landed in trees, and by trees I'm talking 60, 70 foot high pine trees. We did that once up on the, what is it? What's there's a military reservation up near Williams. What's the Navajo? Yeah, we Camp Navajo. We landed in the tree there. We ended up getting thank you. We ended up getting an arborist to come out with his son, and they climbed the trees. This was like at 9 o'clock at night. Climbed the trees to cut them down, and then just to make it fun, our next flight we did up in that area, we flew from Flagstaff, and we ended up in another 50, 60 foot pine tree. This time it was in Kachina Village. Just we caught it. We got part of it. Yeah, between two trees, but it was in a housing community. And the same arborist came out, but this time he brought his cherry picker and got it. So we have fun coming down sometimes, and have had some interesting places. We talked earlier about it. We've landed in. We didn't land in the prison yard, but we did land on prison property out in Florence. That one was kind of fun because one of our members went up to talk to the facility and called back on the radio and basically said they've confirmed it's on property and are going to help us go get it, but the rest of you guys need to go somewhere else because you're making the guards nervous. That's when we realized we were sitting across the street from the entry with several guard towers looking at us through certain optics. But it's definitely it definitely is as much fun where we land sometimes as where we fly.
Okay, we're going to talk a little bit about the balloon physics. I'll give you a couple of numbers, but don't get hung up on them. And I'll tell you right now, I converted everything to cubic feet because cubic feet is more natural for most people in America to think about rather than cubic centimeters and cubic meters and all that kind of stuff. So the balloon at launch, first off, has a natural spherical shape, about 8 feet. Depending upon who you talk to, that may be as high as 10 feet or 12 feet. It is packaged, folded with only a little talcum powder inside to keep the inside surfaces from sticking to each other. There is no air in it to speak of. As we start putting gas in the bottom, the buoyancy of the gas pushes the balloon upward wherever the gas is. We try and help it get to the top of the balloon rather than pooching out on one side and having the balloon half upside down. And as it fills, the buoyancy of the gas pushes the balloon up in the center, and we get a teardrop shape coming down. The more gas we put in, the wider the teardrop gets. Go ahead. Okay, as mentioned in the slide, we use a weight equal to the payload weight plus the overfill. And this is temporarily connected to the filler tube, which is a piece of PVC pipe that is securely fastened inside the neck of the balloon. And it serves two purposes. Number one, during the initial fill procedures, it keeps the base of the balloon anchored all by itself. Once the balloon starts getting up near the weight or the amount of lift that we want, then somebody's got to ride herd on that weight so it doesn't fly away on us. So they've got to hang on to it. Some of the problems we run into, if there's a major wind blowing, we get two effects going on. One is a Venturi effect across the top of the balloon, which tends to give it more lift sitting on the ground. That lift is artificial because when it's in the air, it's blowing with the wind. So there's no specific wind blowing across the top of it. So we confuses whether we've got enough gas in it or not. The other thing is when the wind is pushing sideways on the balloon, it's still trying to move the weight. And for the poor person that's sitting there trying to figure out how much is that sideways motion and how much is lift, in a high wind, that can get very confusing. And that's part of the reason that we're transitioning to the gas flow meters to make sure of how much gas we actually have in the balloon. I don't know. Stephen, you want to mention that?
So if it gets over 8 to 10 miles an hour on the ground, it gets really difficult trying to do it. We've had it happen, but that's when we start getting the balloon tilting over. You're trying to make sure we're not hitting the ground. We've had it hit the ground and stuff. So ideally 10 is definitely very, very rough. 5 is over 5 is we start thinking about whether we're going to do it. The problem is when you start and it's 2 or 3 and you're about 3/4 of the way through the fill and we start getting gusts up there, then you start playing the, and usually what we'll do at launch, especially if we're expecting any winds, is we will get several volunteers, usually students. We'll give them they'll have hard hats and glasses for protection, but we'll give them gloves. We have cotton gloves and we'll basically have them try to help stabilize the balloon and keep it from tilting around too much.
Right. And the cotton gloves protect against fingernails, finger grease, rings. The watches are dangerous. Anything on your hand that might damage that balloon is dangerous because that'll put a flaw in the balloon and it will burst way early. We don't want that. Now, an interesting note here, at launch time, the balloon is not pressurized. Some people don't realize this. Unlike a toy party balloon that when you get it, it's about 1 inch across or maybe 1.5 inches across. And if you very carefully puff a little air in it, you find it's, maybe 1 inch in diameter, and you blow it up and it's 1 foot in diameter. Well, these balloons are somewhere in the neighborhood of 8 to 10 to 12 feet in diameter by their natural design. That's how big the latex package is. And that means that as we put the gas in, when we have the right amount of gas in it, it is still not pressurized. The atmospheric pressure is the same outside the balloon as the gas pressure is inside the balloon. The only forces going on is the gravitational pull of the balloon itself, maybe stretching it just slightly. And we've got our test weight attached to the bottom, so that stretches it downward a little bit. And one of the reasons that I can verify that is I have seen many instances where the quick release fitting, which was screwed into the filler neck, it's a piece of plastic PVC with a cap on it, is threaded for about a 1/2 inch pipe thread, and it's got a standard air pressure quick release fitting plugged into it. So when you disconnect it, it closes off. Doesn't have to, but we don't fly that. We take a wrench and unscrew it from the plastic pipe, set it down, pick up a plastic plug, which is similarly threaded, thread it in, and cinch that with the wrench. There is no major gas flow in or out of that filler neck while that is disconnected, which is further proof we have not put enough gas in the balloon to make it stretch. We've only put enough to get the right amount of gas in the balloon at launch. Now, once we've got that plastic plug in there, then we're set and it's ready to launch. Go ahead to the next slide. That's okay. This is number 4. Okay. So at launch immediately, as you saw in the things, the balloon bounces around a little bit because it's got all this lift and no load because we've disconnected the test weight. And as it gets up and starts picking up the various packages, then it's getting its full load and it stabilizes and everything goes up. And the total weight of the balloon plus the payload and the aerodynamic drag on the balloon, which is critical, because if we had no aerodynamic drag in 2 or 3 minutes, that dude would be supersonic at the rate of force we have on it to accelerate it vertically. So the coefficient of drag is such that if we've got roughly 5 pounds of lift, it will stabilize at around 5 to 6 meters per second, which is around 1,100 or 1,200 feet per minute, which is a nice calm rise time for a small aircraft. Yeah, question over here. We'll get there in a minute. We're getting there. This is takeoff. Now, as at takeoff, typical balloon flight, we've got 18 pounds of payload. We've got 7 pounds for the balloon plus the plastic filler neck. So that's a total of 25 pounds. We have at the air density at about 1,100 or 1,600 feet, we have about 33 pounds of air that we are displacing by the helium or by the hydrogen. It has about a 9-foot diameter, about 450 cubic feet of gas inside it and air that's displaced outside it. The balloon, like I say, is not pressurized. It is merely functioning as a barrier to keep the gases from mixing. And that gives us, 33 pounds of lift minus about 2.5 pounds, or 33 pounds of air minus 2.5 pounds for the hydrogen that is inside the balloon. Gives us about 30.5 pounds of lift, and we got about 25 pounds of total payload. So that's about 5.5 pounds of free lift that is just pushing the whole thing up. Now, as it goes up, the outside air pressure drops. Go ahead and next slide. There's a chart. On the left side, you see it says 1,000 millibars. That is standard atmospheric pressure at standard conditions. Here at 1,100 feet, we're a little under that. We're in the 950, 960 range. As you go up the curve, you can see that as we go up in altitude, the air pressure diminishes. When we hit 90,000 feet, we are in the neighborhood of 20 millibars of air pressure, which is approximately 0.17 psi, pounds per square inch, compared to the 14.7 at takeoff. Okay, so as we go up, the outside air pressure is diminishing. The balloon is expanding because we haven't changed the amount of gas. The balloon is now sealed. So as the outside pressure diminishes, the inside pressure makes the balloon larger. And it reaches an equilibrium, and the equilibrium point keeps moving as it goes up. And so we have 3 forces primarily at work on this. We've got the air pressure outside, we've got the gas pressure inside, and we've got the expansion pressure of the balloon, because now we're starting to stretch the balloon. The minute we get over, I don't know, somewhere in the 10,000 foot range, the outside air pressure has dropped enough that we are beginning to stretch the balloon. And that, to really compute what's going on step by step, there's a lot of numbers that I don't have to make those calculations. But you can see the outside air pressure is dropping significantly. Now at burst, according to the manufacturer's numbers that I found, it's supposed to burst at 43 feet in diameter. And that is approximately 41,629 cubic feet. And at that point, the air density is down in the order of 8.8 times 10 to the minus 4th. And the hydrogen density is down in 6.148 times 10 to the minus 5th. It appears, and my numbers are not complete, but it appears we've got about 34 pounds of lift with the 25-pound payload with the balloon. which means we've got about 9 pounds of free lift instead of 5 pounds of free lift. And the rate of climb just before burst, fortunately, I can go on aprs.fi and I can log in and I can download the flight data for that tracker. And we have serial number or numbers on them so that we can differentiate them. And I can download the data for that tracker for that time period. And I can insert that into an Excel spreadsheet and I can calculate what the incremental rate of climb is for every reading. And the readings are about 30 seconds apart. And I can take 8 or 10 or 15 readings in a group and just take the total time and the total distance and compute what the average rate of climb is. And for this instance, the rate of climb is going to be in the 5 to 5.5 meters per second. And the rate of climb just before burst is in the 9 to 10 meters per second. So it is going about twice as fast going up. Now, there's two possible reasons for this. There's several things going on here. Number one, the balloon is getting larger and its size determines the aerodynamic drag. The balloon is getting larger faster. This is an engineering a design marvel. The guys that make these balloons have designed them so that with a conventional gas, helium or hydrogen inside them, as the balloon gets larger, it displaces a larger volume of air, but the air is getting thinner. The gas inside is getting thinner. And it turns out that the expansion of the balloon is controlled so that the actual rate of climb, the actual lift, is increasing as this thing goes up. It's not decreasing. If it were decreasing, the balloon would go up to some altitude and it would stabilize and it would just float at that altitude until something else happened to it. But once it's got enough lift to actually go up, as it goes up and the gas inside expands, it gets a little bit more lift because the various gases, densities and stuff are just, they're changing in the right direction to increase the lift a little bit. So by the time it gets up to 100,000 feet and it bursts, it's going approximately twice as fast as it was at launch. And this has a good thing for us if we get a short fill, we know it's going to go up and burst somewhere. It's not just going to float around the world a few times. There are other whisper balloons that are designed to go up to like 60,000 feet and stay there for days. And they go around and around and around the earth, and the guys get to record the telemetry every time they come around. So, but that's a different story. Yeah. So, that's number 5. Yeah, typical flights start at about 5 meters per second. And they're typically in the 9 to 10 meter per second just before burst. Go ahead and hit the next slide. This is a chart which is generated off of our prediction spreadsheet that Bob Thompson drew up. And he admitted that the rate of climb, which is the number on the blue curve, was used from empirical data averaged on a few flights, and it is valid for that area between 110 and 120%. I come to the conclusion that there is a second order drag coefficient number coming into play that we don't know about. We don't have a handle on it because I've collected data from flights that were at 150% fill, and this predicts an initial rate of climb of like 8.58, and the highest I've seen on those flights is 6.7, which means there's a little more drag than what we're actually accommodating. However, the sweet spot at 120% is really, really accurate. So we can count on that. And what was mentioned earlier in passing. One of the flights for the eclipse, the partial eclipse in New Mexico, we launched it from a campground just outside Roswell, New Mexico. And it turns out there was some problem with the balloons. I don't know exactly what it was. And that balloon was either way under fill or somewhat, a couple, 3 pounds overweight. I'm not sure which. But myself and Stephen and Bill McLean were about 60 miles downrange. And we were watching the balloon on the trackers, waiting for it to go over. When it went over us, it was at 25,000 feet. It should have been at 75,000 feet. It was about a third up to where it should have been. And I double checked. I've double checked the data recently. That balloon started out at 1.5 meters per second. It should have been about 5. It was running 1.5 meters per second for a rate of climb. So it was 3 times slow.
Well, we kind of figured when the second balloon that launched 25 minutes later passed it at like 20,000 feet. So we kind of knew something was up.
Yeah. So we're out there and we looked at the data real quick, and Stephen made the decision. He said, I made the comment jokingly, that balloon is headed for Lubbock, Texas. We're sitting in New Mexico, and that balloon was headed for Lubbock, Texas. I didn't realize at the time how close I was. So Stephen said, I'll go back and get this other one because it looks like it's going to come down about 5 miles short of where we're at. And you and Bill go get this one. So Bill and I took off and dodged across Texas. And as we crossed into Texas, I noticed the speed limit sign said 75 miles an hour, and the road was a 2-lane farm road. It did have a stripe down the middle of it. But being in that condition, I had my tracking program on the right-hand seat with the screen facing me. But at 75 miles an hour on a 2-lane road, I could not glance at it more than a split second. So Bill's wife was riding with him, and she was a very good navigator, and she had about 3 screens open in front of her. So I would call her for information on where we were going. And we had to dive north and then east and then north and then east because there's no roads in that part of Texas that go northeast. They go north or east or northwest, but nothing goes northeast. So we had to keep jogging over. And at one point, she called me up and she says, that balloon's doing 107 miles an hour. It was in the jet stream. We're doing 75. We're obviously not catching it. It's gaining on us by 30 miles an hour at least. It finally slowed down probably when it burst. I noticed on the tracker that it did a little horseshoe dance right over I-27 due north of Lubbock, Texas. And then it continued in a straight line down from there further east. And we finally caught up with it there. And we got back to camp at 5:30 that afternoon. And I scoped it out. Near as I can tell, that bird came down 140 miles from where it was launched. So I told Stephen, I got a standing issue. The second state line I crossed, that's it, I'm done. But the nice thing is, it appears that with the design of those balloons, if it's got enough lift to actually lift and go someplace off the start line, it will continue up to 100,000 feet and it will burst somewhere up in that area, and it's going to come back down. We don't have to worry about it floating around the world. So let's see. Yeah. Oh, the last slide. The balloon is designed to expand to about 43 feet in diameter before burst, about 100,000 feet. Okay. For a given payload weight, as was mentioned a couple of times already, we can adjust the amount of gas used. We can make it a little less or a little more. If we make it a little more, it goes up faster. It bursts at a lower altitude because it is stretching the balloon sooner. And a little less time to burst, less distance traveled. So it'll shorten the total trip up a little bit. If we put a little less gas in it, it goes up slower. It bursts at a slightly higher altitude, more time to burst and more distance traveled. And in the case of a severe underfill, instead of 60 or 70 miles, we're talking 140. So, and I think that's my last slide. And I will give it back over to Clayton.
Okay, time for the shameless plugs. Please join us as a volunteer if this is something you're interested in. ANSR is led by an entirely volunteer elected board, and all of our launches and events are staffed by a crew of volunteer members. So if you're interested, you can join us. We rely on our members' skill sets to be successful, so we need your skills and your knowledge to help us with our electronics and software and ham radio and balloon recoveries with your off-road vehicles. Membership is open to anyone and gives you a vote in the organization, as well as some member benefits like the gas reimbursement and a couple other things. And the public is welcome to attend any launches. So even if you're not a member of ANSR and you want to come see a launch, please, we publish the launches on our website, and you are always welcome to come out and watch.
Yeah, we won't put you to work unless you ask.
Now, if by chance you love electronics, computers, programming, off-roading, or overlanding with your four-wheel drive vehicle, hiking, ham radio, please let us know. Those are the skill sets we are interested in.
Especially hiking. If you like to go out in the middle of the desert and sometimes a little bit of climbing involved, or that and tree climbing. Anybody's got tree climbing skills, we'd love to have that on the skill set. Best way to look at this is it's if you like geocaching, if you like hiking, we have a great thing for you. We have a geocache. We don't know where it's going to be.
And then last but not least, I will ask for donations. ANSR is funded through access to grant funding as well as contributions from individual supporters. So if you're interested in donating, please let us know. And we would greatly appreciate it. Otherwise, I don't know that we've requested a grant from ARCA. I think because of how much we have available, it becomes a challenge to ask from other ham radio groups. But that's a good idea. And thank you, everybody, to all our donors, supporters, and volunteers for over 20 years of launches and supporting local educational institutions. Thank you. I've got some swag up here if anybody's interested. Sorry for those at home. I can send a few with the club and or get your hands on them, but I've got some patches and stickers for anybody here. And if you want to learn more about us, just visit us at ansr.org.
So we do have a question online. I don't know if Mark is still here with us, but he asked if ANSR would be willing to present at Northern Arizona School Consortium.
That sounds like something we could do. I will say that, so ANSR is just the flight support portion of the experience, but we do potentially, through our partners at Arizona Space Grant, have options for funding for classes or students to get involved in this program as well. So although we're just the launch support, if there are students that want to participate and teachers that want to participate, we can help with access to that funding as well. So absolutely, if you want to shoot me an email, clayton.jacobs@ansr.org, I would be totally willing to look into it. Thank you. Any other questions from the group?
May I interject something real quick, please?
Yeah, go ahead.
Yeah, this is Mark. I'm sorry, this is Mark Christian, WB8 BWC. I missed the email, Clayton, but I sit with the Arizona School Consortium in Northern Arizona. I participate in many of their planning meetings, and I think they might be interested in having a presentation to that consortium at one of their future meetings, because I believe there are many schools represented there that would really jump at the chance to have a science technology-based presentation. They'd probably ask for about an hour or so just to kind of give a brief rundown. So if I can send you an email, that would be great.
That would absolutely work. You can just my name, clayton.jacobs@ansr.org, or you can do info@ansr.org as well, and that'll get to us.
All right, I have that. Thank you.
Thank you. Okay, question in the room. Good. Okay, so the question was, what happens if we don't reach the burst altitude? Normally, there isn't any equipment that is dependent upon reaching a certain altitude. So if we only make it to 60,000 feet, then when the balloon bursts, we attempt to do a real-time repredict of the new landing location, and then we'll start hunting this new landing site. I have in the past, though, seen flights where students might attempt to build a payload or some kind of experiment that would like trigger at 90,000 or trigger at 80,000. And it's interesting because if they base that off of like barometric versus GPS, they might not get the same result. Or if the balloon doesn't make it to that altitude, they won't get any result on the experiment. So, there's different quirks out there.
Yeah, we've had premature bursts, and basically it just ends up causing it shorter. We've also had bursts where, if you saw in the video, if you'll notice how violent it was at burst, how things were jumbling around. There have been a couple of times on occasion where the neck and string from the balloon after burst has wrapped itself up in the parachute, or in one case we even had the entire balloon string wrapped itself up in the parachute. And that one burst at, I think if I remember right, that one burst at like 106, and like about 6-7 minutes later, when we were trying to get the next beacon, somebody gave a report that they got the beacon and it was at 17,000 feet. We were like, what? It dropped like a rock. Huh? We did hit terminal. One of the student payloads had accelerometers on there, and I think they said we hit something like 25 or 30 G. So,
and there is a little hula hoop thing on the chute that we add on the paracord going up to the chute to try to spread the chute open as it falls. But whether that actually is hurt or benefited or harmed when the balloon strings are wrapping around or the pieces of the balloon wrap around it, you never know.
Right. Yeah, that ring, we use a spreader ring. So if you'll notice, we don't try to deploy the parachute. So the balloon in reality is lifting everything by the top of the parachute. So if you ever, when you were a kid, if you took your GI Joe and put the parachute on them and threw them up, that's the same concept. The difference is, like you said, we have that ring in there. That one is to try to help keep the strings from wrapping up, but also to keep it open enough to where it gets air.
Any other questions from the group? Very good. Thank you so much. I'll set out some swag, and thank you, Arizona Airspace Research.
Well, thank you so much, gentlemen. Great presentation. Well, we hope everybody enjoyed this evening's presentation about the Arizona Airspace Research. We look forward to seeing you next month, and hopefully I tentatively have planned for AJ7T, Ron, to come and talk about 1010, and we'll see if he's able to make it. If not, we will figure something else out for next month, but tentatively plan for Ron to come talk about 1010 next month. So thanks for coming this evening, and we'll see you at the next one. Take care. Bye-bye.